This is a major breakthrough in more than one respect. The scientists of the LIGOVirgo Collaboration, which includes the CNRS, have for the first time observed the gravitational waves emitted by the merger of two neutron stars, rather than of two black holes as in previous cases. In another first, the light emitted from the source of gravitational waves was observed in the following hours, days and weeks, by 70 other ground and space-based observatories. This series of observations marks the birth of multi-messenger 1 astronomy, and has produced a wealth of results, including a solution to the mystery of gamma-ray bursts and that of the origin of the heaviest elements such as lead, gold and platinum, as well as new insights into the properties of neutron stars, and an independent measurement of the rate of expansion of the universe. These various findings are described in a dozen scientific articles published on the 16th of October 2017 by a number of researchers from CNRS laboratories, more than 200 for one of the publications, members of the LIGOVirgo Collaboration, and partner astronomy groups. An unprecedented series of events began at 12:41 UTC on the 17th of August 2017 with the detection of a new type of gravitational wave signal. This time, the signal detected was considerably longer than in the case of black hole mergers, around 100 seconds as opposed to a fraction of a second, a sign that the two objects that finally coalesced were different from those previously detected. Detailed analysis of the data showed that the masses of the two objects lay somewhere between 1.1 and 1.6 times the mass of the Sun, corresponding to the mass of neutron stars. Neutron stars are the remains of massive stars. At the end of its life, a giant star explodes, giving rise to a supernova. This extremely luminous phenomenon only lasts from a few days to several weeks. Once it is over, all that remains is a very dense core made up almost entirely of neutrons. A neutron star, although only about the size of a city like London, a teaspoon of the material making it up would weigh around 1 billion tons. Neutron stars are the smallest and densest stars discovered so far. Just like the ordinary stars from which they derive, some of them form pairs, orbiting around each other and gradually getting closer while losing energy in the form of gravitational waves, a process that finally accelerates until they merge. While this scenario was predicted by models, this is the first time it has been confirmed by observation. Almost simultaneously and independently, NASA's Fermi satellite recorded a gamma-ray burst, a very high-energy flash of electromagnetic radiation, and immediately sent out an automatic alert. Although this type of burst is relatively common, about once a week on average, this one was special in that it was detected around 2 seconds after the end of the gravitational wave signal, indicating that the two events were closely connected. In addition, analysis of the data from Fermi showed that it lay within a region of the sky covering 1,100 square degrees, which was compatible with the localization recorded by the Virgo and LIGO detectors. The gamma-ray burst was also detected by the European Space Agency ESA integral satellite. These observations confirmed that at least some short gamma-ray bursts are caused by neutron star mergers. A new astronomy has dawned at the same time. The source was localized in the sky by using the arrival times and amplitude of the signals measured by the 3 gravitational wave detectors, the 2 LIGO detectors in the US and the Virgo detector in Europe. The area thus determined, which covered about 30 square degrees 2 in the Hydra constellation in the southern hemisphere, was tens of times smaller than that determined by Fermi. It was communicated to around 90 partner astronomy groups so that they could point their instruments in that direction. 12 hours later, the 1M2H group using the American SWOPE telescope in Chile announced they had discovered a new bright point of light in the NGC 4993 galaxy, located 130 million light-years from Earth. This finding was rapidly confirmed by other telescopes operating independently. A number of instruments then carried out observations, including the ESOS telescope in Chile and the Hubble Space Telescope. The region was then continuously scanned, and initial analyses of light spectra showed that this was not a supernova but a type of object that had never been seen before, made up of very hot matter in the process of cooling, with rapidly decreasing luminosity, leading to a race against time to observe it before it faded away altogether. According to models, nuclear reactions take place in the matter ejected by the merger of two neutron stars, causing the formation of atomic nuclei heavier than iron such as gold, lead, etc., due to the abundance of neutrons. This very hot, radioactive matter then disperses, emitting light at every wavelength. Initially very blue, this light becomes redder as the matter cools and disperses. Known as a kilonova, this phenomenon, hitherto merely predicted by theory, has now been convincingly confirmed. What is probably the principal process that forms the universe's heaviest elements has therefore now been observed for the first time. as well as confirming that mergers of neutron stars produce short gamma-ray bursts, providing the first unambiguous detection of a kilonova and showing that the universe's heavy elements are formed in this process. This series of observations also provides a better understanding of the physics of neutron stars and makes it possible to rule out certain extreme theoretical models. It also provides a new way of measuring the Hubble constant, which describes the rate of expansion of the universe. These results, which involve various disciplines, nuclear physics, astrophysics, cosmology, gravitation, illustrate the potential of a newly emerging astronomy, based on several types of cosmic messenger gravitational waves, electromagnetic radiation such as light and gamma rays, and perhaps one day particles such as neutrinos and cosmic rays. They are described in a dozen papers, one of which is the work of several thousand researchers gathered together in around 50 collaborations. The LIGOVirgo Collaboration. The Virgo interferometer was built near Pisa about 25 years ago by the French National Centre for Scientific Research (CNRS) and the Italian Istituto Nazionale di Fisica Nucleare (INFN). The Virgo Collaboration consists of more than 280 physicists and engineers belonging to 20 different European research groups, 6 from the CNRS in France, 8 from the INFN in Italy, 2 in the Netherlands with NICEF, the MTA Wigner RCP in Hungary, the POLGRAW group in Poland, Spain with the University of Valencia and the European Gravitational Observatory, EGO, the laboratory hosting the Virgo detector near Pisa in Italy, funded by CNRS, INFN, and NICEF. LIGO is funded by the NSF, and operated by Caltech and MIT, which conceived of LIGO and led the initial and advanced LIGO projects. Financial support for the Advanced LIGO project was led by the NSF with Germany Max Planck Society, the UK Science and Technology Facilities Council and Australian Research Council making significant commitments and contributions to the project. More than 1,200 scientists from around the world participate in the effort through the LIGO.